All right, let's dive into a mathematical tool that is so elegant, it almost feels like a secret code for understanding curves. And the best part? It all starts with something you already know, but it builds into something just incredibly powerful. So let's get right into it.
I mean, think about it, right? A straight line is, well, it's easy. The slope is the same everywhere. Super simple. But a curve? A curve is always changing its mind. It gets steeper over here, then flattens out over there. So the real question is, how in the world do you capture that kind of behavior when you don't even have the equation? All you've got are just a few scattered points on a graph. What do you do? Well, that is the exact puzzle we're going to solve today. And the key, the big answer, is this really powerful idea called the divided difference. This is what's going to let us unlock all the secrets of a curve just by looking at one point at a time.
Okay, so what is a divided difference really? To get our heads around it, we're going to start super simple, like just 2 points. That's it. All right, so here's the formal definition. Now, don't let the notation scare you off, okay? That f of x0, x1, that's just a fancy way of saying, hey, we're looking at 2 points. And the formula itself, it's just the change in the y values divided by the change in the x values. Does that ring a bell? Yeah, if that formula looked familiar, you are absolutely right on the money. It's just the slope, rise over run. That's all it is. The first-order divided difference is literally just the slope of the line that connects our 2 points. And that's the big idea here. We are building this incredibly powerful new concept from something we all learned way back in basic algebra. But that's just with 2 points, right? The real magic, the really cool stuff, happens when we throw in a third point, and then a fourth. This is where divided differences go from being just slope and start to reveal the actual shape of the curve. Okay, let's look at the second-order difference. Now, I know at first glance it looks kind of intimidating, but just look closer at the numerator, the top part of that fraction. What is it? It's just the difference between 2 of those first-order slopes we just calculated. We're literally using our first answer to build our second one. That's the pattern. So here's how you do it step by step. First, you find the slope between your first 2 points, points 0 and 1. Easy enough. Then, you find the slope between your next 2 points, 1 and 2. Got it? Now for the really clever part. You take the difference between those 2 slopes you just found, and for the final step, you just divide all of that by the difference between your outside x values, x0 and x2. It's this awesome, repeatable process. And I bet you can guess what happens next, right? The pattern just keeps on going. For the third-order difference, what do? You take 2 second-order differences, find their difference, and then divide by the total span of the outermost x values. It's the exact same trick, just taken one level higher. You see it, right? This is the recursive heart of the entire idea. It really is like those Russian nesting dolls. Each new calculation is built from the ones that came right before it. Which means, once you get that first step, you basically understand the whole shebang. And of course, all of this builds up to a general formula. But again, please, don't try to memorize this thing. Just see it for what it truly is. It's that same beautiful, simple pattern we've been following all along, just dressed up in some formal language. It's always the difference of the previous level divided by the total range. That's the secret. Okay, so we have this really powerful recursive process. That's great. But, calculating all these things step by step could get kind of messy fast. Luckily for us, mathematicians absolutely love elegant organization, and they came up with the perfect tool for exactly this job. And here it is, the divided difference table. This thing makes everything so much easier. Look, you just pop in your x and y data on the left. Then, to get any value in the table, you just look at the 2 numbers diagonally to its left in the column right before it. You find their difference, divide by the right x span, and bam, you've got your new value. See how every single column is built directly from the one just before it? It turns this whole recursive calculation into a simple visual fill-in-the-blanks puzzle. It's fantastic. All right, now let's talk about a really neat property of these divided differences. Seriously, it's kind of like a mathematical magic trick, and it turns out to be incredibly important. So what's this magic trick? It's symmetry. Plain and simple. What it means is that the order of the points you use just doesn't matter at all. Calculating the difference using point A, then point B gives you the exact same answer as if you'd used point B, then point A. And yeah, that might seem simple, but believe me, it has some huge implications. And we can see why this works really easily just by looking at the first-order case. Check out the calculation for f of x1, x0. Now, what happens if you multiply both the top and the bottom by -1? You get the exact same formula for f of x0, x1. They are mathematically identical. Pretty cool, right?
And here's the thing, this isn't just some weird quirk of the first order. Nope. As the source material confirms, this symmetry holds true no matter how many points you're working with. You can shuffle the order of your arguments any way you want, and the result will always be the same. That's what makes this a seriously robust and super reliable tool. Okay, so we've built this elegant, recursive, and totally symmetric tool. But why? I mean, what's the actual point of all this? Well, this is where things get really exciting, because this is where we connect this abstract idea back to some of the biggest concepts in all of mathematics. And the first major reason it matters so much is its profound connection to one of the absolute cornerstones of mathematics, calculus. And here it is, the first massive connection. Go back to our simple slope formula. Now imagine taking those 2 points on a curve and just sliding them closer and closer and even closer together until they're infinitesimally close, until they've basically become a single point. What have you just found? You found the derivative. That's the instantaneous slope, right out of calculus. Our divided difference is literally the bridge that connects a few simple data points to the absolute core idea of calculus.
Okay, the second huge reason this matters is what it reveals about polynomials. You know, those functions we all know and love, like x squared or x cubed.
This property is genuinely amazing, and it's like a powerful detective tool for data. Just think about it. Say you have a bunch of messy data points, and you have no idea what kind of relationship they have. Well, you can just throw them into a divided difference table. If the second-order differences all turn into the same constant number, boom, you know you're looking at a quadratic. If the third-order differences are all constant, you've got a cubic. The divided differences can literally reveal the secret, underlying nature of your data. So we started with just a simple idea, slope. And through this incredibly clever, recursive pattern, we built a tool that bridges the gap between discrete points, algebra, and all the way to calculus. It really makes you wonder, doesn't it? What other profound mathematical truths are just hiding out there in plain sight, just waiting to be discovered, all built on the simplest of ideas? Thanks for tuning into this explainer.